Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Central University of Haryana. Today we are going to discuss about a module, addition of angular momenta and the Clebsch-Gordon coefficients under the paper Quantum Mechanics 1. The main points that we are going to be covering in this module are: number 1, vector addition of the two independent angular momenta, importance of total angular momentum considering the role of central and non-central potentials, the possibility of the two possible representations called uncoupled and coupled representations, and finally we are going to be discussing the representations, that is coupled and uncoupled representations, and how these are related to what are called as the Clebsch-Gordon coefficients. Angular momentum plays a crucial role in determining the state of a particle. The various components of the angular momentum help us in determining the state of the particle, and correspondingly we are able to find out the eigenvalues and the eigenvectors, where we use the angular momentum operators. Similarly, in order to determine the state of a system consisting of maybe two non-interacting particles or interacting particles, or even if we are considering the angular momentum coming from two different components like the orbital angular momentum and the intrinsic spin of the same particle, the total angular momentum needs to be evaluated for the entire system. For this, it is imperative to discuss the rules that govern the addition of the angular momenta. The non-interacting and the interacting particle scenario, which comprise of a system, that is, that whether the system is made up of non-interacting particles, then how do we do this addition, and in case of interacting particles, how do we make the formalism. Then the coupled and the non-coupled representation, and finally we will investigate these representations, that is the coupled and the non-coupled, using the Clebsch-Gordon coefficients. Addition of two angular momenta. Now, in order to find out the addition of two angular momenta, let us start with two independent angular momentum operators, operator J1 and operator J2, which commute with each other, that is, they satisfy the commutation relation commutator of operator J1 and J2 is equal to 0. Or if we expand this relation, what we get is J1 operator J2 minus operator J2 operator J1 is equal to 0. These angular momenta may refer to different particles or to independent systems, or it might also be that these two different angular momenta might refer to the two different angular momentum that exist in the electron, that is the orbital angular momentum operator L and the spin angular momentum denoted by operator S. So in this manner, operators J1 and J2 can represent the angular momentum of two different particles of two independent systems, or even two different types of angular momenta that exist for a single particle or a single electron. Now, if we take the state vector for the first angular momentum, that is state vector J1 M1, where J1 is the angular momentum and M1 is the corresponding magnetic quantum number associated with this angular momentum, then state vector J1 M1 or the ket vector J1 M1 can be normalized to simultaneous eigenstates of operator J1 square and operator J1Z, where operator J1 is the total angular momentum for state 1, and operator J1Z is the Z component of the angular momentum for the state J1. And using these two relations, or rather using operators J1 and J1Z operating on the ket vector J1M1 or the state J1M1, we get the usual relations, that is operator J1 square acting on state vector J1M1 gives us H cross square J1 times J1 plus 1 into the state vector J1M1, where H cross square J1 times J1 plus 1 is the eigenvalue corresponding to the operator J1 square, and H cross is H by 2 pi, and H is the Planck's constant. Similarly, when operator J1Z acts on the state vector J1M1, then it yields an eigenvalue M1 H cross acting on the state vector J1M1, where H cross has been defined earlier. In a similar manner, we can also find out the eigenvalues for operator J2 square and J2Z acting on the ket vector J2M2. And in case of these, that is in case of the total angular momentum J2, these turn out to be operator J2 square acting on J2M2 ket vector yields H cross square J2 times J2 plus 1 acting on ket vector J2M2, where H cross square J2 times J2 plus 1 within brackets is the eigenvalue and J2M2 is the corresponding eigenstate. Similarly, operator J2Z acting on the ket vector J2M2 yields the eigenvalue M2H cross and the eigenstate J2M2. Uncoupled representation. Now, if we look at the normalized simultaneous eigenstates of the two different total angular momentum operators, that is J1 and J2, we have the eigenvalue for the eigenstate of the operator J1 square as H cross square J1 times within brackets J1 plus 1. The eigenvalue corresponding to the operator J2 square is H cross square times J2 times within brackets J2 plus 1, and the eigenvalue corresponding to the operator J1Z acting on the eigenstate J1M1 is M1 times H cross, and the eigenvalue corresponding to the operator J2Z acting on the eigenstate J2M2 is M2 times H cross. And this can be obtained by taking the direct product of the states ket vector J1M1 and ket vector J2M2, that is ket vector J1 J2 M1 M2 is equal to ket vector J1 M1 times ket vector J2 M2. Uncoupled representation. In many situations of physical interest, we deal with the system whose Hamiltonian operator H is invariant under rotations and therefore commutes with the total angular momentum operator J, which is obtained by the addition of the two angular momentum operators J1 and J2, where J1 and J2 represent the total angular momentum operators of particle 1 and particle 2 respectively, or they might even represent the different components of the total angular momentum, like the orbital angular momentum component and the spin angular momentum component. So let us first examine the importance of the total angular momentum, which has so crucial a role to play to introduce the couple representation, or the ket vector R1 vector, R2 vector, where R1 vector and R2 vector represent the position vectors of these two non-interacting particles, and the Hamiltonian for these non-interacting particles is represented by operator H0 is equal to operator H1 plus operator H2, where operator H0 is the Hamiltonian of the total system. Operator H1 corresponds to the Hamiltonian of the first non-interacting particle, and operator H2 corresponds to the Hamiltonian of the second non-interacting particle, where operator H1 is given by the relation minus H cross square by 2 mu1 times del 1 square plus operator VR1 as a function of vector R1. Here H cross square is equal to H by 2 pi, and H is the Planck's constant. Mu1 is the reduced mass of the first particle. Del 1 is the del operator for the first particle having position vector R1, and V as a function of R1 vector is the potential energy corresponding to the first particle having position vector R1. Similarly, the operator H2, the Hamiltonian operator H2 associated with the second particle is given by the relation minus H cross square by 2 mu2 del 2 square plus V as a function of vector R2, where again H cross square is H by 2 pi and H is the Planck's constant. Mu2 is the mass of the second particle. Del 2 is the del operator corresponding to the second particle having position vector R2, and V as a function of position vector R2 is the potential energy associated with the second particle. So if here, since mu1 and mu2 are the masses of the two particles and V as a function of R is the central potential to which each of them are subjected to, then in such a case we can write the commutation relation operator L1, that is commutation relation of operator L1 and operator H1 is equal to 0, which means that the commutation relation of the orbital angular momentum operator L1 and the Hamiltonian H1 corresponding to the first particle is 0. Similarly, the commutation relation of the orbital angular momentum operator L2 and the corresponding Hamiltonian of the second particle H2 also comes out to be 0. In other words, three components of the orbital angular momentum operator L1 and the orbital angular momentum operator L2 corresponding to the first and second particle respectively are constants of motion. Two-particle system with central potential. Now let us assume that the two particles that we have been discussing interact and the two-particle potential energy is given by the function V as a function of R1 vector minus R2 vector. So here we are changing slightly from assuming the two particles to be non-interacting to assuming that the two particles are now interacting, and therefore the potential energy we are taking now is, rather than being the individual potential energy of the particles, it is now the potential energy represented for the combined system, and which is a function of R1 vector minus R2 vector, that is, which is basically a function of the distance between the two particles and does not depend independently on the position vectors of individual particles, but depends on the relative distance of the two particles. So for such a system, the Hamiltonian of the system is given by the relation operator H is equal to operator H1 plus operator H2 plus V as a function of modulus of vector R1 minus vector R2, where the operator H1 is the Hamiltonian corresponding to particle 1, the operator H2 is the Hamiltonian corresponding to particle 2, and V as a function of modulus of position vector R1 minus position vector R2 is the potential of the combined system. So now the commutation relation of the orbital angular momentum operator L1 with h, that means the orbital angular momentum operator of particle 1 with the total Hamiltonian h is given as commutator of operator L1 and h is equal to commutator of operator L1 and v as a function of modulus of r1 vector minus r2 vector. So if we look at this commutation relation, what we see is that the commutation relation of the orbital angular momentum operator of the first particle with the total Hamiltonian operator of the combined system is simply the commutation relation between the orbital angular momentum operator of the first particle and the combined potential energy of the system as a function of modulus of position vector r1 minus position vector r2. Similarly, if we write the commutation relation for the z component of the orbital angular momentum operator of the first particle, it appears as commutation relation for between orbital angular momentum operator L1z and the Hamiltonian operator h is equal to commutation relation between orbital angular momentum operator L1z and the potential energy operator as a function of modulus of r1 vector minus r2 vector, and this is given by minus iota times h cross times within bracket x1 times partial derivative of the total potential with respect to y1 coordinate minus y1 times partial derivative of the total potential with respect to the x1 coordinate. And this commutation relation is generally not zero, which means that the orbital angular momentum operator L1z, that is the z component of the orbital angular momentum operator of the first particle, and the potential of the total system, potential energy of the total system, does not generally commute. Thus, the orbital angular momentum operator L1 is no longer a constant of motion if the two particles are interacting. However, if we define the total orbital angular momentum of this combined system as operator L is equal to operator L1 plus operator L2, where operator L1 corresponds to the orbital angular momentum operator for particle 1 and operator L2 corresponds to the orbital angular momentum operator for particle 2, we find that its components are constants of motion. So let us look at this through an example. Let us consider the commutation relation of the z component of the total orbital angular momentum operator, that is Lz, and the total Hamiltonian, that is h. So this commutation relation can be written as the commutation relation between the sum of the orbital angular momentum operator L1z and orbital angular momentum operator L2z. That means this commutation relation can be viewed as the commutation relation between the sum of the z components of the individual orbital angular momentum operators and the total Hamiltonian h. And if we further expand this commutation relation, the expression that we get is that the commutation relation of the sum of the z components of the orbital angular momentum operators of the two particles and the total Hamiltonian h is given by minus iota times h cross times bracket open x1 times partial derivative of the total potential energy with respect to coordinate y1 minus y1 times partial derivative of the total potential energy with respect to the coordinate x1 plus x2 times partial derivative of the total potential energy of the system with respect to coordinate y2 minus y2 times partial derivative of the total potential energy of the system with respect to coordinate x2. Now, since the total potential energy of the system is a function of the modulus of the position vector r1 minus position vector r2, we can write the partial derivative of the total potential energy with respect to the coordinate x1 as v prime times partial derivative of the modulus of position vector r1 minus position vector r2 with respect to the coordinate x1, and this yields the result v prime times x1 minus x2 upon modulus of position vector r1 minus position vector r2. Similarly, if we find out the partial derivative of the total potential energy of the system with respect to the coordinate x2, we get v prime times partial derivative of the modulus of the position vector r1 minus position vector r2 with respect to coordinate x2, and this turns out to be equal to v prime times x2 minus x1 upon modulus of the position vector r1 minus position vector r2. In a similar manner, we can evaluate the partial derivatives of the potential energy with respect to coordinate y1 and coordinate y2 also. And plugging all these values back in the relation that we had defined above for the commutation relation between the sum of the z component of the orbital angular momentum operators of the two individual particles and the total Hamiltonian, the final result that we get is that the z component of the total angular momentum operator and the total Hamiltonian H, the commutation relation of these two quantities yields minus iota times h cross times v prime by modulus of r1 position vector minus r2 position vector, the whole times bracket open x1 times within brackets y1 minus y2 minus y1 times within brackets x1 minus x2 plus x2 times within bracket y2 minus y1 minus y2 times within bracket x2 minus x1. And this, as we can see, works out to be equal to 0, which means what premise we had started with, that the total angular momentum operator, that is the total orbital angular momentum operator L of this combined system, is a constant of motion. Hamiltonian with spin orbit term. Now, if we consider that the particle, apart from having the orbital angular momentum, also has the spin angular momentum, that means that the particle, apart from having orbital term, also has the spin, intrinsic spin term, or has the intrinsic spin, then we come across a situation where the potential can no longer be defined as a function of only the relative distance between the two particles, and the potential energy now is non-central. So what we mean by non-central is that apart from being a function of the relative distance between the two position vectors, the potential energy now depends on the other terms also. And when we consider the spin term, intrinsic spin term also, then the Hamiltonian that defines the spin orbit coupling term is defined as the spin orbit Hamiltonian operator is equal to xi as a function of r times operator L dot operator S, or xi as a function of r times the scalar product of the orbital angular momentum operator L with the spin angular momentum operator S, where xi r is a known function of the position vector r. In such a case, the orbital angular momentum vector operator L and the spin angular momentum vector operator S no longer commute with the total Hamiltonian. For example, if we look at the commutation relation for the z component of the total orbital angular momentum operator L with the Hamiltonian operator for the spin orbit coupling term, the relation that comes out is commutation relation of operator Lz with the Hamiltonian operator SO, which is the Hamiltonian operator for the spin orbit coupling term, is equal to xi as a function of r times the commutation relation of the z component of the total orbital angular momentum operator, that is operator Lz, with the sum of the x component of the orbital angular momentum operator times the spin angular momentum operator and the y component of the orbital angular momentum operator times the y component of the spin angular momentum operator and the z component of the orbital angular momentum operator times the z component of the spin angular momentum operator. In a similar manner, we can also write down the relation for the commutation relation between the z component of the spin angular momentum operator with the Hamiltonian operator for the spin orbit coupling term, and this turns out to be equal to xi as a function of r times the commutation relation of the z component of the spin angular momentum operator with the sum of the x components of the orbital angular momentum operator times the spin angular momentum operator and the y component of the orbital angular momentum operator times the spin angular momentum operators and the z components of the orbital angular momentum operator times the spin angular momentum operator. That means xi r times the commutation relation of the operator Sz with operator Lx times operator Sx plus operator Ly times operator Sy plus operator Lz times operator Sz. So in case of the commutation relation of the z component of the orbital angular momentum operator Lz with the spin orbit term of the total Hamiltonian operator HSO, the final result turns out to be xi as a function of r times within brackets I h cross operator Ly times operator Sx minus I h cross times operator Lx times operator Sy, and as we can see that this term is not equal to 0 generally. Similarly, for the commutation relation between the z component of the spin angular momentum operator Sz with the total Hamiltonian operator spin orbit coupling term, that is HSO, turns out to be xi as a function of r times bracket open I h cross Lx times Sy minus I h cross times Ly times Sx, where Lx and Ly are the x and the y component of the orbital angular momentum operator respectively, and Sx and Sy operators are the x and the y component of the spin angular momentum operators respectively. Total angular momentum J, constant of motion. Now the total angular momentum J is given as the sum of the orbital angular momentum L and the total spin angular momentum S. All the three components of the total angular momentum J are constants of motion. Thus, if we take the commutation relation between Jz, that is the z component of the total angular momentum, and the spin orbit coupling component of the Hamiltonian operator, the commutation relation comes out to be equal to that between the sum of the z component of the orbital angular momentum operator and the z component of the spin angular momentum operator and the spin orbit coupling component of the Hamiltonian operator, and this commutator is equal to 0. which is also true for other components. From this discussion, we can see that in situations where we have two angular momenta, that is the orbital angular momentum operator L and the spin angular momentum operator S here, but henceforth we shall call J1 and J2, which are the total angular momentum operator for particle 1 and particle 2, which commute and are in general not constants of motion. In such cases, we look for the eigenstates of the total Hamiltonian operator, which are simultaneous eigenstates of the total angular momentum operator square, that is the square of j square operator, and the z component of the total angular momentum operator, that is operator jz. Now, the total angular momentum operator j of the system is the vector sum of the two commutating angular momenta, that is angular momentum operator j1 and angular momentum operator j2, corresponding to the particles 1 and 2, where the total angular momentum operator j is the sum of the angular momentum operator j1 corresponding to particle 1 and the total angular momentum operator j2 corresponding to particle 2. Two possible representations. The operator j square, which is given by the relation operator j square is equal to operator j1 plus operator j2 whole square, and this can be expanded to give operator j1 square plus operator j2 square plus twice operator j1 dot operator j2, and this can further be expanded to give us the relation operator j1 square plus operator j2 square plus twice operator j1x times operator j2x plus twice operator j1y times operator j2y plus twice operator j1z times operator j2z, where the dot product of operator j1 and j2 has been expanded in all the three components of the total angular momentum j, that is the x, the y and the z components. Now, since all the components of the total angular momentum associated with the first particle, that is operator j1, commute with those of the total angular momentum operator j2, and also the commutation of operator j1 square with operator j1 is equal to the commutation of operator j2 square with operator j2 is equal to 0, which means that not only do all the components of the total angular momentum operator j1 commute with the total angular momentum operator j2 of the two particles 1 and 2 respectively, but even the square of the total angular momentum operator j1 commutes with the operator j1, and similarly the square of the total angular momentum operator j2 commutes with the operator j2. Thus, it follows that the total angular momentum operator j2 square commutes with both. It follows that the square of the total angular momentum operator, that is j square, commutes with the square of the total angular momentum operator of the first particle, that is j1 square, and the square of the total angular momentum operator of the second particle, that is j2 square. However, as the z component of the total angular momentum operator of the first particle does not commute with the x or the y components of the total angular momentum operator, we find that the square of the total angular momentum operator does not commute with the z component of the total angular momentum operator of the first particle, that is j1z, and for the same reason it also does not commute with the total angular momentum operator z component of the second particle, that is j2z. And because of these observations, what we find is that the simultaneous eigenstates of the J square operator, that is the square of the total angular momentum operator, and the Z component of the total angular momentum operator, that is Jz, are the eigenstates of the J1 square operator and J2 square operator, that is the square of the total angular momentum operator for the first particle and the square of the total angular momentum operator of the second particle, but do not in general have simultaneous eigenstates with the Z components of the total angular momentum operator of the first particle and the second particle. Coupled and uncoupled representations. Now let us look at the Clebsch-Gordon coefficients. We find there are two distinct descriptions that we can have for the system that we have been discussing. The first description is in terms of the eigenstates of the operators J1 square, J2 square, J1z and J2z, as has been discussed previously, where the operators J1 square and J1z are the square of the total angular momentum operator and its z component, while the operators J2 square and J2z are the square of the total angular momentum operator and its z component for the second particle. There is another distinct description that we can have in terms of the eigenstates of the operators J1 square, J2 square, J square and Jz, where J1 square is the square of the total angular momentum operator of the first particle, J2 square is the square of the total angular momentum operator of the second particle, J square is the square of the total angular momentum operator of the combined system, and Jz is the z component of the total angular momentum operator of the combined system. Now let us denote the basis vectors in case of the second description, which involves J1 square operator, operator J2 square, operator J square and operator Jz, by the state vectors or the basis vectors J1, J2, Jm, and sometimes this is also denoted by the state vector or the eigen or the basis vector Jm. So using this basis vector representation, we then have, if we want to find out the corresponding eigenstates of these basis vectors with respect to the different operators, we have operator J1 square acting on the basis vectors J1, J2, J and M yields the eigenvalue H cross square times J1 times within brackets J1 plus 1 times the basis vector J1, J2, J and M. Similarly, the operator J2 square acting on the basis vectors J1, J2, J, M yields the eigenvalue H cross square times J2 times within brackets J2 plus 1 times the basis vectors J1, J2, J, M, and the total angular momentum operator square operator, that is J square acting on the basis vectors J1, J2, J, M yields the eigenvalue H cross square times J times within brackets J plus 1 times operator J1, vector J1, J2, J and M, and the Z component of the total angular momentum operator operating on the basis vectors J1, J2, J, M yields the eigenvalue H cross M times eigenvector J1, J2, J, M. This representation is called the coupled representation, and since the two representations that we have discussed above, that means the representation involving the state vectors or the basis vectors j1, j2, jm and the basis vectors j1, j2, m1 and m2 are simply orthonormal bases in the same Hilbert space, Clebsch-Gordon coefficients. Now, if we look at the two representations described by the basis vectors j1, j2, jm and the basis vectors j1, j2, m1, m2, we find that the two bases are orthonormal in the same Hilbert space and that they are related by the unitary transformations given by basis vector j1, j2, jm is equivalent to writing basis vector jm, which turns out to be equal to summation over all values of m1, m2, bra vector j1, j2, m1, m2, ket vector jm, ket vector j1, m1, ket vector j2, m2. Now, as m1 can take 2j1 plus 1 different values, and similarly for a given value of j2, m2 can take 2j2 plus 1 different values, the dimensionality of the representation of the above equation is 2j1 plus 1 times 2j2 plus 1. Here the summation is over all values of m1 and m2. The coefficient which occurred in the summation, that is bra vector j1, j2, m1, m2, ket vector jm, depend on the 6 angular momentum quantum numbers, that is j1, j2, m1, m2, j and m, and these coefficients are called the Clebsch-Gordon coefficients or vector coefficients, and these Clebsch-Gordon coefficients have different symbols and names used for it, and over here we shall, in this module and in the modules to follow, we shall use the symbol capital C, subscript m1, m2, m, superscript j1, j2, j, and we shall be calling it the CG or C coefficients. So students, now let us summarize what all we have learned in this module. So, firstly, we learnt about the vector addition of two independent angular momenta, wherein we started by considering two independent particles and then we found out the vector addition of the two angular momenta components corresponding to those two independent particles. From there, we moved on to a somewhat more complex situation where the particles were interacting rather than being non-interacting. And the major difference that this made to our formalism was that the potential, which in case of non-interacting particles or independent angular momenta was central in nature, now becomes non-central in nature. Then we learned about the possibility of two possible representations called uncoupled and coupled representations. And finally, using these representations, that is the coupled representation and the uncoupled representations, we tried to find out the relation between them and the Clebsch-Gordon coefficients. Thank you.